So, Mike, you're the guy that puts the focal plane together. You know, the part that people don't think about when they look at a telescope.
Right.
I think most people are not aware of what actually happens at the back end. They have some misty, romantic notion that we still put our eyes to telescopes, but we don't. Why don't we? Why don't we look through telescopes anymore?
I would say in the early 80s, we went digital with our almost all astronomical focal planes. The reason for that is that they're just much more efficient. We can get a lot more photons collected than your eye can see. In the old days, we used photographic plates, and they were just a few percent efficient, meaning that 98% or 97% of the light is lost.
Right.
And a few percent is detected, and now it's the other way
around.
And
that was a fundamental limit. There's like no way you can make photographic emulsion better than it was.
A lot of work went into it over the years. Astronomers worked with Kodak for many years to improve it. They did all kinds of chemical processes, and I think sometimes they could get 10% efficiency. But a good modern detector now converts light into a signal at about 90% or 95% efficiency. Yeah. So it's really a matter of being efficient and not having to use either your eye where you remember things or photographic plates where you have to go through the chemical processes.
Right. And I guess also photographic emulsions are not nearly as uniform, or
that's right. And they're typically on glass. You have to there's a handling issue. There's a lot of chemicals to develop them. They're kind of fun in the old days, but nowadays it's all digital.
I've been in this game long enough that when I was a grad student, I was in Australia taking sky survey plates and hypersensitizing 3AJ emulsions. And there was a myth back in those days that you'll appreciate as a detector dude, that there was one guy in Kodak with the squeegee who could get it more uniform than anyone else, and he did all the astronomical plates.
That's right. Exactly right.
So what was the inception of CCDs? When did they really, were they a military product that moved into the commercial sector? Where did they really come from?
They were developed at Bell Laboratories, and I want to say around the late 60s. And they were first used as a memory chip. The idea was that you would store electrical signal in what we now think of as pixels, which are the same as the elements on a television or a computer monitor. But this is in silicon, and it would be a way to store any kind of electrical signal, like an oscilloscope tracing or output from some kind of signal analyzer. But they soon realized that if you shine light on the silicon, using the photoelectric effect is something that converts photons into electrons, and they can be stored in those same pixels, and you get a two-dimensional image. And that was really the beginning of what CCDs have replaced almost all other detectors at the time, by converting light into a two-dimensional image.
Now, that was an interesting time, of course, for Bell Labs. So was this really blue skies research where they didn't know, or were they aiming for a particular product when they were trying to develop this?
I'm not absolutely sure, but I think they were aiming for a product to store signals in an oscilloscope.
Okay, so what came out? So this was an amazing outcome, really.
Yes, it really was, and it really changed all imaging, because from that point on, things just moved more and more towards digital, including television, these days. And,
and there's the great story. I remember when they got the Nobel Prize a couple of years ago. The Willard and Boyce, I can't remember. I think those are the two names of the engineers. So they were on the verge of being shut down. They were doing their little project and it wasn't clear it was getting anywhere, and they, over lunch they came up with a back illuminated CCD idea, which is pretty cool. I'm sure they couldn't have anticipated.
That's right.
So as this left Bell Labs and started, how did it get known by astronomers and used for the first time?
I'm not sure where the first time it was used, but I think one of the main, in the early 80s, I was an undergraduate at UCLA in 1980, and I remember one of the first talks about using this digital detector called a CCD instead of a photographic plate at the University of California telescopes. So it was just starting in the 80s. So I'd say in the late 70s, people started realizing that they could be reasonably efficient devices.
And as I recall, almost none of the original vendors and people manufacturing them still do so.
That's right. That's right. The problem is that for the kind of efficiency that astronomers like, where we really, you can either build bigger telescopes or you can make more efficient detectors, but you can't make the stars brighter. So the problem is, to make your detectors efficient, it's very expensive, and that really has distinguished the what we call the back illuminated devices and the ultraviolet sensitive devices from the kind that might be in a home camcorder or previously in a cell phone. Nowadays, CCDs are being replaced by things called CMOS imagers. And the expense of making the very efficient detectors is something that most companies try to do for a few years and then they stop.
And of course, our market is pretty small.
It's very small. There's just not that many observatories around.
Right.
My interest in CCDs actually came from a graduate class that I took here at the University of Arizona that Roger Angel taught. And he asked that question. He said, what can we as astronomers do to make back illuminated detectors available to our community, because vendors keep, they try for a year or two and they decide there's no money in it and they stop. So that actually was a graduate project I did, and then that eventually led to my dissertation, and I'm still doing that now.
Right.
And it's the same issue. Companies still come and go. I would say there's very few companies that stay in this business for very long.
Right.
The market for camcorders and cell phones is huge, and that's where the money is. And, and there's lots of technology developed for that, and that does help us because we can use the kind of equipment that the semiconductor industry uses to make memory chips and Pentium processors and everything else. And we do take advantage of that, but it's still kind of an art to make the backside parts.
So let's just back off and talk about how does a astronomy grade or type CCD, how does it work?
Okay, so the overall process is to focus light onto the detector surface. The detector is always made of silicon.
And these are physically pretty small.
It's very small. A big detector is just a few inches across. They're made on silicon wafers. CCDs are made on 6-inch diameter wafers. That's as large as they are. The state-of-the-art wafers these days, which are mostly in the major fabs like Intel and several companies in Japan, that's 12 inches diameter. So CCDs are not made on the latest technology, and they probably won't be because of the expense to do the CCD process. There's a long formula. It's several hundred steps of taking a silicon wafer and turning it into any kind of integrated circuit. And the CCD is just a particular one that has a large number of pixels. Typical and HD TV is small, the pixels are 15 microns, so they're smaller than a diameter of a human hair. But something that's HD TV is maybe 1,000 by 1,000 pixels, and the state of the art in astronomy is 10,000 by 10,000. So that's the equivalent of a 111 megapixel camera. So they're actually extremely large, very expensive, but still just kind of smaller than a sheet of paper. And so you focus light onto the detector with a standard lens, and it can be a telescope or it can be a camera lens, depends on what the use is. And by dividing the silicon up into a grid of pixels, you can then shift the charge. You create electrons under each pixel, and by using what's called a controller, you send a sequence of voltages to the silicon, and you move the charge around from one pixel to the next. And that's why it's called a charge-coupled device, a CCD, because each pixel is coupled to the next pixel.
I see. Okay.
And by using electronics, you can actually make that charge transfer very fast. And you typically shift, a lot of times you can think of a CCD as a square piece of silicon, and you shift the charge to the corners. So maybe there's an amplifier that takes the charge as it comes in a sequence from each pixel and turns it into a voltage, which is then just amplified by camera electronics and eventually digitized and put all back together onto a computer monitor or stored as an image on disk.
And in terms of, the mental image, of course, is like a bucket brigade. So presumably you don't want to spill electrons.
That's right.
That's a requirement.
So different CCDs have different architectures, but the most common in astronomy is called a full frame transfer device. And what that just means is there's actually no shutter on the device. So you somewhere mechanically you open a shutter, you focus your galaxy or stars onto the device, and you let it sit there for a long time. That's the integration period. And by doing that, all the photons that hit the device are stored up, and you can take exposures some people take exposures that are as long as an hour. One of the problems with taking very long exposures is because the material is silicon, it's sensitive to cosmic rays.
Mm-hmm.
And so you tend to corrupt your image with cosmic rays,
Right.
which look to be like events that you could easily confuse for stars.
Right.
So a lot of times you'll take multiple exposures of 10 or 15 minutes each.
Right.
It depends a lot on what you're doing.
And when people, as an aside, I remember when people see what a raw Hubble Space Telescope image looks
terrible,
like,
yeah.
it's scary because the
That's right.
cosmic rays are not blocked by the
That's
atmosphere.
right. One of the very nice things about digital imaging is that you have the data stored in a computer and you can manipulate the data.
Mm-hmm.
And that's not a bad thing. You can average multiple frames together, multiple images, and you can get rid of the noise to some extent. So you can make images that the raw data is very ugly, but you can turn them into very nice pictures.
Right. And apart from quantum efficiency, obviously the percentage of incoming photons converted into electrons, that's now very high, right? 90% or higher?
Yeah, that's right.
Across the whole optical range?
Yeah, all optical. As you get towards the near infrared, just a little bit further to the red than your eye can see, then typically the light starts to penetrate all the way through the silicon because its thickness is maybe anywhere between 10 and 100 microns. So that's very, very thin. And the red light, actually, the photons, there's a probability that the light will get through the device and just come out the backside, so it won't be detected. So the efficiency drops in the red.
Right.
When you get towards a 1 micron wavelength, which is quite a bit redder than your eye can see, then the infrared detectors, which is a different technology, become much more efficient. And so farther in the infrared, you use infrared detectors. In the visible and towards the ultraviolet and even the X-rays, you use silicon detectors, which are mostly CCDs these days. They are sensitive to X-rays. If you've ever had a dental digital X-ray, then that is a little CCD that they're usually putting in your mouth. And the reason to do that is it's more efficient than film, so you can have a lower dosage of X-rays, and that's a good thing.
Now, this sensitivity and high sensitivity across wavelength, I know that's a thing that astronomers crave, and that's also special sauce you bring to what you do. So to talk about how that works, how do you optimize these things?
Yeah. So the idea of taking a normal CCD, which is made at a fabrication facility, which is usually called a fab, you have a silicon wafer, and it's got one or more CCDs on it. The trick that was come up quite a long time ago, and certainly in the early 70s, was you could take a device and you could take a CCD and flip it upside down and shine the light in the backside. And if you do that and you make the device thin enough, then you get a very high efficiency. And the reason for that is the photons don't reflect off the surface if you treat the back surface with an antireflection coating, which is very similar to what people have on their eyeglasses or on the windows of buildings. It just decreases the reflection. And also, if you can make the device thin enough where the light can still, the photons still get into the front side area of the CCD where the pixels are. And so that's a lot of times a back illuminated CCD is called a thin CCD. And the technology is fairly expensive. This backside device is much more expensive than a front side device. But basically what you do is you take the silicon wafer, you flip it upside down, and you bond it so that the front side is against some kind of support. And then you chemically etch the silicon away till it's a different thickness, but we'll just say 10 or 20 microns in thickness. And then because you flip the device upside down, you typically have indium or gold bumps that make electrical contact to the signals that you require to either get the signal out or to manipulate those voltages so that you can do the bucket brigade shifting. And then a lot of times you'll put an antireflection coating on the back surface to get the efficiency as high as possible at where you're interested. Some devices will be optimized for the blue, some of them will be optimized for the red. And then you take that device and you put it into a package that has wires connected to it, and you stick that into a camera. So because there's an etching process involved, you have a chemistry lab that's involved in doing this. So in order to etch the silicon, we use a combination of hydrofluoric, nitric, and acetic acid. And the reason for that is that...
and you look quite normal, but you've been exposed to these things for decades.
That's right. Nothing grows in the lab because it's all going to die.
Okay, right.
So it's basically a big bubbling bath of acid. You drop the silicon in it, and it takes about 2 hours to etch down to the thickness that we need. We protect the device with wax. We actually have a computer-controlled wax machine that dispenses hot wax. And basically, you put a pattern on the device that you don't want to etch, and you drop it in this acid bath, and all the exposed silicon drops down. It's in some ways, it's a lot like developing photographic plates in the old days. It's just an acid mixture.
So when did you have your first? I mean, you've moved towards almost an industrial grade operation because you make so many devices, but you must have started small, right? And you were figuring this out as you went along.
That's right. As I mentioned, I started doing it as a class project here at Stewart, and then what happened was there were several observatories that were interested in trying to see if we could make them back illuminated CCDs for their own telescopes. I mean, Stewart was one of them. We did early work with Lick Observatory in California, a couple of places that are now part of ESO in Europe. And they funded us to try to, get this process down where we could make reasonably good detectors, and that worked. We started doing sort of 1,000 by 1,000 pixel arrays, and it quickly got to 2,000 by 2,000, and then eventually 4,000 by 4,000 is kind of a standard still. It's still a very large detector, and then there's these specialty cases of 10,000 by 10,000. But yeah, we started doing the work both for our telescopes, but I also was working with NASA on for the Hubble Space Telescope and developing the coatings, these antireflection coatings. And we were trying to, in that case, because Hubble's out in space, we were optimizing for the ultraviolet. And
so which detectors were these?
These are on the Advanced Camera for Survey one. So we actually did backup detectors for ACS in case the primary vendor, which was a commercial company, didn't succeed. They did succeed, so our devices didn't fly on Hubble, but a lot of the coatings that we developed are used for those devices. And what's interesting about that is that we got pretty good at making ultraviolet sensitive CCDs, which are not something that are used on ground-based telescopes because the atmosphere absorbs the ultraviolet light. But it turns out that if you want to inspect semiconductors, what you want to do is do it at very short wavelengths, because you need to illuminate your light or illuminate your object with light that has a wavelength that's shorter than
the size
feature
of your wires and everything.
Your wires, And as integrated circuits got smaller and smaller, they needed shorter and shorter light, which is more towards the ultraviolet. So all of a sudden we got a new business that had nothing to do with astronomy, but it was a direct spin-off of work that we did for NASA and astronomy.
Sounds like you should have just spun off a company and become a mogul, but you're still an astronomer.
No, it's too much fun. There's lots of experimenting to do. But because of that, we actually make more industrial imaging detectors in my lab here than we do astronomy detectors. And they're almost the same. The difference is what kind of cameras they're used in. The technology is the same, but they're ultraviolet optimized. And one of the interesting things about the industrial imaging cameras is you kind of have to think of an assembly line, and you have a camera that's looking at the objects on the assembly line, which are typically wafers, and they illuminate the wafer with a laser. So it's hit with an ultraviolet laser, so you have very short wavelength light. The camera takes a picture, and then the computer goes off and analyzes whether there's any defects. And so they're just inspecting all the time. But because assembly lines need to move fast, so you can make billions of processors and memory chips, the cameras are extremely fast. They run at gigapixels per second come out, which is something that astronomers are only now starting to dream about for the big projects like LSST to read that many pixels. But they do it routinely, but they don't do it at the precision that astronomers do. The noise is higher, and the number of bits of converted data is typically smaller. But there's a lot of experience running extremely fast CCDs, and they actually heat up because I didn't mention it, but because silicon generates its own charge at room temperature. Most astronomical cameras are cooled with liquid nitrogen. That gets them to about minus 100 Celsius, and for these cameras that run so fast for industrial imaging, they actually heat, and they're at like plus 60 C, so they have to read really fast just because they would be swamped by the signal that silicon generates, which is called dark current.
So that, just to talk a bit more about that, I mean, that's one of the key figures of merit for astronomy, is the the dark current, or the floor on the charge, just because of the temperature of the camera and the background and so on. And that's incredibly low now, right?
It is very low. A good detector running at minus 100 Celsius will generate just a few electrons per pixel per hour. So if you took an hour exposure with the shutter closed, so there's no starlight or anything getting on the device, you'd only see a few electrons, because each photon we try to generate one electron. In that signal. It's very low. In the old days, those numbers would have been hundreds.
And the key, I guess, is you want that signal, that sort of unavoidable but low signal, to be less than what's going to come from the sky, the dark sky that you're looking at.
That's right.
And that's easily satisfied these days.
If you cool, yes.
If you cool.
And so if you have an amateur astronomy system, which is generally not as expensive as the professional ones, they may cool to maybe minus 40 or minus 50 C.
So like a thermoelectric
cooler, yeah. And so those are simpler. They don't have to have liquid nitrogen. You just apply a voltage and you cool the part, but they'll have higher dark current, which is okay, because all you have to do is get enough signal onto your detector and understand it's the signal to noise ratio. That's the other issue, is that there is a noise associated with reading a device. So read noise is the other, like dark current, the other figure of merit that's important. When CCD started, there was a noise associated with the reading of every pixel that was several hundred electrons.
So you just didn't do it very often.
Just didn't do it, yeah. And you had to have very bright signals. You might have, if you had 100 photons creating 100 electrons, and your noise is 100, your signal to noise is 1, and it's a very grainy image. It looks terrible. Nowadays, there are 1 electron read noise devices. Typical devices are under 5, but you just get a few electrons of noise.
And to give a reference for that, what's the dynamic range? What's the full well? How many electrons do you get before it saturates?
A good number is 100,000 for a typical pixel. The larger the pixels, the more electrons they can hold. But typical astronomy pixels are 15 microns, and most 100,000 electrons with 2 or 3 electrons read noise, and that gives you a dynamic range of 30,000 or something like that, which is much higher than photographic plates. I'm actually not sure what it is, but I think they're 1,000 or something like that.
So let's talk about big, because it seems like when you have a detector that, with your help over the years and the demands of astronomy, has become almost perfect, all those gains have already been made, right? And now people want bigger, right? They want to tile these things. And,
that's right.
And what's the current state of the art of tiling a focal plane?
We call that mosaics of CCDs, and there are several mosaics out there. But basically what you do is you take a device and you try to make it so that it's what's called its fill factor is as large as possible, and that is the ratio of the total area of the detector to the active pixels, the light-sensitive pixels. And what that really means is that you want to have very small edges around your device, and then you put multiple parts together in a focal plane. You make a grid of CCDs. Each one reads out to its own electronics, and there are focal planes that have 30 or 40 devices in them now, and there are, I think, the Pan-STARRS project at University of Hawaii has 64, I believe, detectors. So less than 100 CCDs put together into a focal plane is kind of state of the art these days. That's still a very expensive, very large focal plane to do that. People are talking about putting together 10 to 20 of the big 10K by 10K devices, which would be similar in size.
And so these are multi-gigapixels. Yes,
that's right. I think the Pan-STARRS is a gigapixel camera, and the next one is the LSST, the Large Sidereal Synoptic Telescope, and that's 3 billion pixels.
Right.
And that would be about 200 detectors, something like that.
Right.
And that's definitely, over the next 10 years, that's kind of what we anticipate as state of the art.
Right. Now sort of paint a picture, because I know that when this game started and the CCDs were small, the Dewar, the cryostat was the coffee pot size. Well, what are we talking about for these big cameras?
I guess about a meter in size now.
Right.
So, more than 3 feet across.
Right. And at that point, you have some real issues of cooling everything in the electronics, and which must generate a lot of heat too, right?
That's right. So one of the things that people are talking about is making the electronics as digital as possible so that they don't have the analog circuits which generate more heat.
Mm-hmm.
So the idea is to convert the voltage that comes off the CCD to a digital signal as soon as possible. And they're talking about having the dewar, which is the vacuum vessel that holds the liquid nitrogen or other cooling mechanism, and the focal plane, to have essentially digital signals come out. Bits go right into some computer interface rather than voltages to reduce the heat. When you have a window, because when you cool your device, because it's so cold, if it goes below 0 C, where water freezes, you would condense all over the device, and you don't ever want to do that. So you have a vacuum typically in these vessels. And if you just imagine a meter diameter piece of glass with a vacuum behind it, there's a huge force pushing on it because it's 15 pounds per square inch of atmospheric pressure. And so the windows have to be very thick. People have talked about filling the dewars with a gas that has low thermal conductivity like argon. So there's a lot of technology associated with the cryogenics and the vacuum technology to get these big focal planes, and they're huge. I mean, they weigh thousands of pounds and extremely expensive.
But the typical, these are state-of-the-art devices, of course, but the more typical CCD workhorse CCD is the major observatories. It's a pretty turnkey operation, right? They're not. I mean, I remember using them in the 70s and early 80s when they were like, sports car like a Ferrari or a Lamborghini. They did this great thing, and they would break, or you couldn't trust them. But now they're pretty.
That's right. There are several companies that make the electronics. So the big components are the detector itself, the dewar that holds it, that it has probably a thermoelectric cooler for the smaller end, and then the electronics. And the electronics now, for modern professional observatories, that might be $10,000 to $20,000 for the electronics that interfaces to the computer and to the CCD. But for a few $1,000s, there are companies that make very nice systems that have low noise, and they'll cool a device, and they're quite small. They have a USB interface. They're very popular with amateur astronomers, and they're really as good as CCDs have been for professional observers for a very long time. The kind of things an amateur can get today, we would have loved to have 10 years ago or 15 years ago.
And of course, you're responsible for one of the problems of astronomers of the data deluge.
That's right.
So put a sort of number on that. I mean, when you hit the button to take a picture with, say, one of these big mosaics, you're talking about a lot.
Yeah. So a modern device, which is still a big one, is 4,000 by 4,000 pixels. So that's 16 million pixels. We typically digitize to 2 bytes or 16 bits per pixel. So that's 32 megabytes for just one image. When I started and used to drive up to Kitt Peak, we would take discs with us that held 5 images, and they were in a suitcase that were 2 feet across. And now, of course, you can have a USB stick that has 32 gigabytes on it. So even though the detectors are very large, the cost of memory has come down, and the ability for computers to handle the data has come down. But it's still a major achievement. I mean, when you think about the digitization of the whole sky and manipulating it, it still uses a lot of computer processing power and a lot of memory.
And it's kind of scary when you read that LSST that you've just already talked about is because it's federally funded and sort of a public taxpayer resource. They're committed to putting everything out there for the public, like online overnight or something. That's an incredible shoveling of data exercise.
That's right. And they'll probably only store it at a few locations. But in the future, you can easily imagine that if you wanted to have access to the whole survey of the sky, you could download it onto your own set of disks. It may be multiple disks, but it's not. It won't be that big a deal in the future. Right now, it's going to be centered at computing stations, like superconductor facilities. But we're really just talking about a few racks of equipment to do this.
Now, just a little aside, because I mean CCDs are the standard and perfect, almost perfect detector for astronomers. But I remember some years ago, people talked about other things, mamas and papas and
Right.
other type. Are there any other detectors that astronomers like that have special purposes or niches?
Well, there's a couple things. The big thing that we have to mention is CMOS imagers, and CMOS imagers are what are in most cell phones nowadays, and they're an offshoot of CCDs. Basically, as the industry, the semiconductor industry, learned how to make CCDs and silicon detectors, they started to realize that they could make imagers a lot like they make memory chips, where each pixel can be addressed with logic. And so it's a different process, but it's still silicon. And they're now making CMOS imagers that are several thousand pixels on a side. The noise is dropping down. It's typically higher than CCDs, but just like CCDs over time, it's dropping. And as you can tell by how many cell phones have cameras, and most camcorders now are CMOS imagers, they're slowly replacing, maybe I should say quickly replacing CCDs now. It's taken a long time since they were first developed. But I would say that in the future, we may not have CCDs, and we would have CMOS imagers that are just as efficient as what CCDs are now.
So they're in the commercial sector, but not yet in the astronomy research sector.
Not quite, but in my lab, we are doing quite a bit of back illuminated CMOS work now, and that's new. That's turning on, where people are starting to try to use them for scientific applications.
Right.
So I think it'll follow the same evolution. There'll be expensive CMOS imagers that are back illuminated and have the backside coatings and have low noise, and those will still be fairly expensive, but they'll be very desirable. One of the issues is that because the process of making a CCD at the fab is different, than CMOS imaging. Eventually, fabs won't maintain a CCD process because there won't be enough customers in the world, and they'll make these fabs cost like billions of dollars for the facility. So there'll probably be a time when you just can't get CCDs, and hopefully CMOS will be good enough. One of the problems we face is that the pixels for CMOS imagers are very small. Most people probably don't realize that the pixel in their cell phone camera is less than 2 microns in size. Wow. So the dynamic range is very small because they can't hold many electrons. Right. And that's a problem that astronomers have to face, that we may only have reasonable cost detectors with very small pixels. And
that will put extra big demands on the quality of the optics.
That's right.
Too.
Right. To make optics of a high enough quality over the large areas that telescopes require is a very daunting task at this point.
So I know that the full list would take too long, but just you've made devices for an awful lot of different observatories. I mean, just give a sense of the range of places that have your devices sitting in the back end of their telescope.
I'd say a large number of the astronomical telescopes in the world. We've made CCDs for Keck Observatory in Hawaii, quite a few of the telescopes at ESO, which is the European Southern Observatory. Those are in Chile. All of the University of Arizona telescopes, Mount Palomar, which used to be the largest telescope in the world. Recently, we just had one of our 10K by 10K devices go to Antarctica to be in the telescope that was developed there by the Chinese National Observatory. So that was our 7th continent. Oh. So we have a device on every continent. We have Africa. SAO, yes, down in southern Africa. Yeah. So it took a long time. We had detectors on 6 continents for quite a few years, but I've really been waiting.
I hope you keep a map in your office.
In the lab, there's a map with pins on it.
With pins, okay.
Yeah, so most places.
So some people travel and put pins in the map. You have CCDs and you put pins in the map.
That's right, yeah.
And what about, I guess with the CMOS, you talked a little bit about the future, but if you're just projecting ahead, I mean, what you're doing is R&D, basically. Right. So you must keep your eye out on where it's headed or what the next steps for you are.
I think there's still interest in larger and larger detectors. That just seems always to be of interest, and also faster detectors. Because CCDs are read out, pixel by pixel in a sense, you do want to read them very quickly. So there is development work in how to make electrons move faster through the silicon. So there's some interesting technology developments. You can also do that by having more outputs. So instead of having just the 4 corners where you bring the signal out, you could have our 10K device has 16 outputs, and so there's dividing the devices into sections, and that's one of the technologies. Another interesting thing we've done this last 2 years is we've made curve detectors where we bend the silicon. The reason for that is that you can relax the specifications on the optics if you can allow the focal plane that the optics have to focus to be curved. You can either have a more efficient focal plane with smaller, better focusing with it's a smaller point spread function, it's called, or you could have less optics to do the same job, which makes it cheaper. And so curve detectors, certainly mosaics, and the ability to butt devices closer together with less and less gap, by increasing the fill factor, that's of interest. Extending to the ultraviolet, the common lasers on the short side are 193 nanometers. The next generation of integrated circuits is looking like it'll be somewhere around 157 nanometers. So that means the devices have to be sensitive to even farther in the ultraviolet. That's a problem because as you move farther the ultraviolet, there's so much energy, lasers damage the silicon. And so a lot of work is going into how to keep the devices from basically frying as they get illuminated. So there's that. I would say I don't see anything that isn't silicon for the standard devices. The technology for silicon is so advanced because of semiconductor computers that it's hard to see something else. But there are certainly other materials that are able to convert light to electricity. It could be that there are other materials coming, but I don't think there's a lot of active work on it.
So even after all this time, there's still flavor left in the gum.
That's right.
Yeah. That's great. Well, thanks for talking to me, Mike.
Sure. Thanks, Chris.